sometimes I'll start off with something like this in the test. 2 over 6 minus 5 over 18, 5 over 54, minus 11 over 162. I used to see these things in, oh yeah, I said that and wrote the other thing, didn't I? Thank you. Uh, yeah, oh golly, get off to a good start here, don't I? When I see these things in public articles and so forth, these sequences, I always find myself not real good at figuring out what is the general pattern, but that's what I asked you here. Find the nth term, what is the pattern? And I'm not going to try and be tricky on this stuff. Typically what happens is either you've got something where you add the same thing every term, or you've got something where you multiply the same thing every term is a common trick. There are other things, but it's supposed to be straightforward so you can recognize what the pattern is. And here I'll look on the top on the numerator. I'm adding 3 to the numerator's absolute value at least each time. And on the bottom, I'm multiplying each one by 3, right? So if I'm adding 3 to the top each time and multiplying 3 on the bottom each time, then what is the nth term here? I think I'm off the camera. I better turn this just a little. I can't. All right, so what's the nth term? What you do is you say this is a sequence where the nth term, in order to get the first term, you have to get 2, but then they differ by 3, so it's going to be something, it's going to be n plus some 3n plus something on the top, right? So that adds 3 each term. And so you just have to figure out what this is. To get 2 on the first one, you have to put minus 1, right? So this will add 3 to each numerator, starting with 2, right? So that's how you get the numerator. If you add 3 each time, then it's just 3 times n plus something. Now, if each one is multiplied by n on the bottom of what I do, I say it'd be each one's multiplied by 3. There's a 3 to the n here times something to get the first term. And so if I get, for the first term, 3 to the 1 times 2 will give me 6. That'll give me the bottom, right? So 2 times 3 to the 1 gives me 6. The first term, 2 times 3 squared, gives me the second term, 2 times 3 cubed. So if you multiply each term by n, then it's just a number times whatever the multiplier is to the n. In this case, 2 times 3 to the n. And if you add the same thing to each number, then it's just whatever the additive thing is times n plus a number. And so you can get it that way. And then if they alternate sign, plus, minus, then you just stick in here in the front, minus 1 to the n if you want the first term to be negative, or minus 1 to the n plus 1, or n minus 1. It doesn't matter. The book likes n minus 1. I like n plus 1. To make them alternate signs. So now I've got plus, minus from that, and these all add 3 to the top. These all multiply 3 on the bottom. That's really as tricky as I want to be on sequences. And that's part A, is to find the nth term. So the sequence of AN, let's say AN is this. And then if you put parentheses around it, the whole thing is this sequence, minus 1 to the n plus 1, 3n minus 1 over 2 times 3 to the n. N equals 1 to infinity. If you leave off the 1 to infinity, then that's assumed. See, I'm just off the screen. I know I can't see all this thing blocking. I guess I think this is visible. Yeah, okay. Sorry, part of my screen is blocked on there. Sometimes I can't tell if it's showing. All right, any questions on that one, 2A? Let's suppose I said find the limit of a sequence here. What about on 2B? When I say the limit of a sequence, that means find the limit of the nth term. So you're just taking limit of this sequence, 2n plus 1, n minus 1, 7n minus 1, and 3n plus 5. what is the limit of that sequence? N equals 1 to infinity assumed on there. All that means is you take the limit from calculus 1 as n goes to infinity of 2n plus 1, n minus 1 over 7n minus 1, 3n plus 5. And the biggest theorem we had for this was if this limit holds for a corresponding real variable x, gives you a finite number, then it's also true for a discrete variable n. And so what you typically want to do here, let me see if I erase the top part. I'm sorry, I'm going to be a little constrained by trying to put this online today. Is just say, well, if this was x instead of n, and it gives me the same number, then I know what the limit is there. So I'll take the limit as x goes to infinity of 2x plus 1, a real variable, x minus 1, 7x minus 1, 3x plus 5, and say this is the limit n goes to infinity. And for polynomials, which is what these are, right? When you multiply them out, it's a number times the whole power of x plus a number times the whole power of x plus dot, 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 plus a number. That's called a polynomial. When you have a polynomial divided by a polynomial, the limit only depends on the dominant terms of the top and bottom, right? And if the top has a higher power, then the limit doesn't exist. It's either infinity or minus infinity or bounces back and forth. If the power of the bottom, the denominator is higher than the limit 0, and if it's the same, then it's the quotient of dominant terms, right? So you, if you multiply this out, you take the by FOIL, you get 2x squared plus a bunch of other stuff. I don't even care if this is very complicated. I just take the dominant term. That means the highest power term. And on the bottom, I'm going to get 21x squared plus a bunch of other stuff. Since the powers are the same, it's the quotient of these dominant terms, and you can cancel the x squares, and you just get 2 over 21 is the limit. All right? So you just take the coefficients of the highest powers when the highest powers match. So it's as easy as that. Just use calculus 1. Questions on that one? All right. How about this one then? Take care of these sequences. I think this is still plugged in. Pulling on it. How about 3a? Use appropriate limit laws and theorems to determine the limit of the sequences. Again, the major law there is to just treat it as though it's calculus 1 and say, what's the limit as n goes to infinity of 3 times n to the 4 over n? So here I'm trying to force you to be proficient with your calculus 1 techniques. How do I evaluate that limit? Yeah. Yeah, so this tends towards 0. Yeah, you get infinity to 0. It's not necessarily 1. It could be infinity. It could be 0. It could be anything in between, actually. This is what we call an indeterminate form. Might be 1. If you see one of these indeterminate forms, like 1 to the infinity, or 0 to the 0, or infinity to the 1, not infinity to the 1, infinity to the 0, like this, those kinds of things, or infinity minus infinity, those kind of things. What you want to do usually is L'Hopital's rule. I'm going to try and write this as follows. I'm going to take n to the 4 over n. When you see it's a power like this, I'm going to use this trick. I'm going to write e to the natural log of n to the 4 over n. This is my trick. I like the way it's done. Some books use logarithmic differentiation for this, but I like this way, which amounts to the same thing. So I'll write e to the ln of anything or inverse functions so they can do each other. This is still n to the 4 over n, right? That's just algebra. But now the exponent comes down, so this is limit Sorry if I'm blocking you move. I know I'm kind of getting in your way. Please don't feel obligated to stay there today. I just can't. I've got dinosaur headphones on here. I need a wire. Limit n goes to infinity of 3 times e to the 4 over n natural log of n, right? Just by properties of logarithms, I can pull the exponent down. Now, the limit of a continuous function, provided the limit turns out to exist, can be pulled inside the continuous function. So the 3 automatically comes out. You can pull a 3 out front, right? A constant outside the limit in any case, whether the limit exists or not. But now the exponential function is a continuous function, so I'm going to pull the limit in here tentatively. And if this limit of its exponent turns out to exist, then this limit exists and is equal to the same value. Okay, so what good did that do? Pull the limit inside the exponential. Because now I turned it into the limit of a quotient, I can apply L'Hopital's rule. That's the idea, right? So that's how you deal with these indeterminate forms where you have an 1 to the infinity or infinity to the 0 or something like that. Now L'Hopital's rule says since I've got this going to infinity over this going to infinity, you only apply L'Hopital's rule if it's infinity over infinity or 0 over 0, right? Or plus or minus on the infinity works. You can now take the limit of the derivative of the top over the derivative of the bottom and say it's 3 times e to the limit n goes to infinity of the derivative of the top, 4 times 1 over n, over the derivative of the bottom, 1. And now we see what's going on, right? This is going to be a good guess today, isn't it? 3e to the, I can pull the 4 out, limit n goes to infinity of 1 over n. And I know that's 0, right? The bottom's going to infinity, the top is going to 1. Since it's fixed number over larger and larger numbers, the quotient is 0. So this is 3 times e to the 4 times 0 is e to the 0 is 1. So this limit is actually equal to 3. How about that? So in some sense, you were right. This case, infinity to the 0 is approaching 1. And then there's a 3 multiplier. On the test, you have to show it, right? And I might make it a little trickier, so maybe this doesn't approach 1, maybe. But that's how you can prove that one. Use L'Hopital's rule. How about the next one? I don't want to spend too much time on sequences, but the idea on sequences is mostly you appeal to some of your limit laws from Calculus 1. Some of them are obvious. Like, how about 3c? What's the limit of 0.99 to the n? Now, you can do the same trick as before to establish it, but any b to the n with any base between 0 and 1, the limit is automatically 0, right? Because b to the n looks like this, or b to the x, you recall, looks like this. This is intuition, but y equals b to the x grows like that. It's exponential growth, and as x goes to minus infinity, its limit is 0. As x goes to infinity, its limit is infinity. This is for b greater than 1. But if you have y equals b to the x with b between 0 and 1, then it's exponential decay. So this is b to the n or b to the x if you do the corresponding real function. So this b to the n one is just discrete dots on this b to the x here. And because the base is less than 1, 0.99 is between 0 and 1. tells you that this limit is automatically 0. So this one you just, oh, I did it again. I keep hitting that thing every time I come across. Should put it up a little higher. So this one, it suffices for me for you just to say that it's b to the n, the limit of an exponential with base between 0 and 1 is 0 because it's exponentially decays. You can apply L'Hopital's rule again to prove this, and there's nothing wrong with that. But I'll just say if it's a b to the x function, you can just write that immediately. All right. So on 3c, I would just do that. Say it's b to the n is one of these decaying exponentials. On 3b, then, suppose I have the limit n goes to infinity of ln of, this thing got messed up, didn't it? N squared minus 1. I was trying to make sure it wasn't wrong there. N squared minus 1 minus, I think. Messed it up when I knocked that off, didn't I? That's right. Trouble with these things is they try and help you so much sometimes you have to keep adjusting them. It's helping me again. Gosh, I just got it right. Adjusted it too much. Oh. Okay, so now you can read it. Minus ln of n squared minus n. 7n squared minus n. How about that one? How do I take the limit of this one? Yeah, use your natural log rules. Yeah, so write that limit n goes to infinity. Very good. Natural log of n squared minus 1 over 7n squared minus n. Log of the difference is the difference of logarithms is the log of the quotient. And then what? Yeah, logarithms are a continuous function. So provided the limit exists, and when you get infinity or minus infinity, you can pull the limit inside and say that this is ln of the limit as n goes to infinity of n squared minus 1 over 7n squared minus n. And now you observe that this is quotient of polynomial, so you take the quotient of the same degree. So you take the quotient of dominant terms and you get 1/7. So this is natural log of 1/7. So this limit does exist as 1/7, and that justifies that you pull the limit inside then. All right. So there's problem 3. That's probably all I want to do on sequences unless you want to see something else. Be able to do problems like that, right? Then one of the difficult things about this, oh, it helped me again. My biggest complaint about Microsoft Word. One of the biggest difficulties is there's so much deja vu going on because there's similar series. There's only two techniques we had. One was for telescoping series and one was for geometric series, right? So for this one, does it look like a geometric series? A geometric series is an a times r to the n series, n equals 0 to infinity. It can be written in this form. It doesn't look like this can be written in that form, so I don't think it's geometric. It must be telescoping since it's the only other kind I gave you. The other thing I can do is give you a sum of two series, each of which is geometric or telescoping, like this one. If you break the sum of the series of the sum into the sum of two series, this series is geometric and this series is geometric, and you can just apply the geometric series theorem twice, for instance. Well, let's try this one first. This one does not look geometric, so I'm going to try telescoping. What I'm going to do is apply partial fractions to rewrite this, and I'll say 2 over n plus 1 n plus 3 I know is equal to something over n plus 1 plus something over n plus 3. You can use your expand command on your calculator, right? You're allowed to bring a calculator to the exam if you want, or you can do it by hand. It's not too bad, right? We did it before for integrals, so I won't go through the details, but suffice to say that 2 over n plus 1 n plus 3 is equal to 1 over n plus 1 plus minus 1 over n plus 3, right? Multiply this one top and bottom by n plus 3, and you've got n plus 3 in the top. Multiply this one top and bottom by n plus 1, and you get n plus 1 on the top. So n plus 3 minus n minus 1 gives you 2 left all over this if you put these over a common denominator, so you can check it too. Okay, so by partial fractions, you can rewrite it like this. And now what you do is, given that you want to calculate that sum, you can do it by first calculating the nth partial sum, right? The sum of these first n terms. With the first term, when n equals 0, you get 1 over 1 plus minus 1 over 3. So you get 1 over 1 minus 1 over 3. Then when n equals 1, you've got 1 over 2 minus 1 over 4. When n equals 3, you've got 1 over 3 minus 1 over 5. And you start to see the pattern 1 over 4 minus 1 over 6. And then the last term has to look like this. If you're going to go to S capital N, you just replace this little n by capital N. And the last term was 1 over capital N plus 1. Am I off the, I think I can see, yeah. Minus 1 over capital N plus 3. And you can write a couple previous terms. The previous one of this, each of these would be 1 less. So it'll be 1 over capital N minus 1 over capital N plus 2. 1 over capital N minus 1 plus 1 over capital N plus 1. Okay, and so this is the whole thing all written out, the sum of the first n terms. And now once you write it with partial fractions form, you notice after the first two terms, things start to cancel, right? The minus 1/3 cancels the plus 1/3. Minus 1/4 cancels the plus 1/4. And the next one, minus 1/5 cancels the plus 1/5. Minus 1/6 cancels the plus 1/6. And so you just have the first half of the first two terms. Similarly, on the back end of the train here, right? Let's see, the 1 over n plus 1 here cancels the, I wrote it wrong here. This is minus. Cancels the minus 1 over n plus 1. And similarly, the minus 1 over n plus 2, let's see, that's not the right one. This one stays, 1 over n plus 2. I keep trying to do that. The minus 1 over n, the left ones on this end cancel the previous term, and the minus 1 over n plus 1 cancels this one, and then everything collapses in the middle. It telescopes, right? Leaving at the end here just 1 plus a half, and then 2 on this end and 2 on that end. Minus 1 over n plus 2, minus 1 over n plus 3. There it is. So there's the nth partial sum. And how do I deduce the sum of the series from that? I'm sorry, it's getting a little low, isn't it? This is kind of an important problem because it illustrates something. S, the sum of the series, by definition, is the limit as n goes to infinity, the nth partial sum. That's the limit of the sequence, right? Had that epsilon definition that we had, which followed limits in calculus 1. But the limit of a series is defined to be the limit of the sequence of partial sums. So we've got a sequence of partial sums, each term of which looks like this. So it's the limit, the sequence limit as n goes to infinity of this thing. 1 plus a half minus 1 over n plus 2 minus 1 over n plus 3. And we notice as n goes to infinity, we get 1 over larger and larger numbers. That goes to 0, and same thing here. So we're just left with 1 plus 1/2 is 3/2. Oops. So the limit of this sequence, if we added up enough terms, we'd see it gets closer and closer to 1.5. That reminds you also how we define the limit of a series, or the sum of a series. It's the limit of the sequence of partial sums where you add up just n terms, right? Any questions on that one? You do that on the test? So that's if you get a telescoping series, you try and collapse everything in the middle and just have one term on each end, or two terms on each end, or three terms on each end, something like that. Right? How about the next one on there? Suppose I did 5b. I already mentioned a little bit on that. Sum should be n equals 0 to infinity, minus 5 to the n over 7 to the n, plus 2 over 3 to the n. How about that one? Just think every one of these is telescoping your geometric or the sum thereof. This one, what you do is you rewrite it as the sum of the sums is the sum of the sums theorem. This is sum n equals 0 to infinity, minus 5 to the n over 7 to the n, plus sum n equals 0 to infinity of 2 over 3 to the n, by the theorem that says if these converge, then the number they converge to is the same as this one. So we'll see if these converge, do they? What kind of series are they? Hmm? Yeah, these are geometric series. Each term multiplied by the same number, just like geometric sequences is each term multiplied by the same number. So I could treat this as sum n. It has to start at n equals 0, right? So if it doesn't, then you can re-index it to start as 0. If I trick you in the test, put n equals 1 to infinity, you have to re-index it by making a change of index. I should have put it that way in here just to test you, huh? It's 1 times minus 5/7 to the n. I can rewrite it that way, right? And this one I can write sum n equals 0 to infinity of 2 times 1/3 to the n. And now it's a times r to the n, a times r to the n. Remember, these converge if and only if absolute value of r is less than 1. So this one converges to 1 over 1 minus a negative 5/7. Right? And this one converges to a, which is 2. Think of this as a times r to the n over 1 minus a third. So let's see, I get 1 over 12/7 is 7/12. And this one, 2 over 2/3, right, is 3. So I've got apparently 43/12. Hopefully that's the answer in the back, where you can check your answers on these. Right, when you do the problems at home, if you need to move, please feel free to move. I'm sorry. Trying to record this is making it hard to see, I know. Okay, so there's how to do a geometric series, or in this case, a sum of two geometric series put into one. Sometimes we're only interested in, does a series converge or not, right? And that will be much more general. We won't just do telescoping or geometric series. Oh, by the way, on this last one, 1 over 2n minus 1, how about that one? Does this one converge? Sum 1 over 2n minus 1. This is a good illustration too. N equals 1 to infinity I did on this one. Does that converge? How do I know on this one? If it converges, then I have to put the sum, and this isn't geometric or telescoping actually, but maybe that's a hint. What you can do with this is say, in here, each term, 1 over 2n minus 1 is greater than 1 over 2n, right? Because it's got a smaller denominator. It's a bigger quotient, right? And the sum n equals 1 to infinity of 1 over 2n, does that converge or diverge? What? Diverges. How do we know it diverges? You can pull a multiplier out, right? This is 1/2. Hope this is not going off. Maybe better make sure. Yeah, it's on. It's 1/2. The constant multiplies. You can't pull n out, but you can pull any constant out. Sum what? N equals 1 to infinity of 1 over n. What's the sum n equals 1 to infinity of 1 over n? Yeah, this is a harmonic series that sums to infinity, right? P equals 1 series or harmonic series, two names for the same thing. This one goes to infinity, so this goes to 1/2 of infinity is still infinity. So this series that we have is bigger than the sum n equals 1 to infinity of 1 over 2 to the n, which is infinity. So this series diverges by the direct comparison test, or just the comparison test is what a lot of books say. So if you see a series that has polynomial divided by polynomial, often the comparison tests are good because the ratio test and the root test don't tend to work for those. You need factorials and powers for those to work. That's where a lot of intuition comes in just from practicing, right? So when you see polynomials, maybe you do a comparison test to see if it converges or not. But for these general polynomials, we don't know how to find their total sums. We did mention a couple of them just for fun, but in general, we don't know what they are. All right, so let's look at some power series here. Suppose I give you one of these power series and I just said, find the radius and interval of convergence, right? Not what they converge to, but just what's the interval. We know that every power series does one of three things, right? Uh, well, every series does one of three things. It either converges absolutely, it converges conditionally, or it diverges. And these power series will always converge, however, absolutely within their radius of convergence and diverge outside the radius of convergence. And at the radius of convergence, they can converge or diverge or neither. So let's look at 4a here. And I say find the radius r of convergence of a power series and the corresponding interval of convergence. This is one of my favorite examples because it's kind of simple. That should be n equals 1 to infinity. 5 times x to the n over n times 2 to the n. How about that one? What's the radius of convergence and the interval of convergence for this series without asking what is its sum? For the interval and radius of convergence, almost always what you want to do is the ratio test. So for these power series, these are the series in powers of x minus a number to the n, right? Try the ratio test. That's almost always what you want to use. The reason being that a lot of these have factorials in them. All of them have powers, right? That's why it's a power series. It's x minus some number to the nth. Here it's x minus 0 to the nth power. And the quotients in the ratio test tend to cancel, so it's a nice test. So we'll try the ratio test with that in mind. The ratio test says you take the limit as n goes to infinity, the absolute value of the nth term, n plus first term over the nth term. And if that is less than 1, you have absolute convergence. If it's greater than 1, you diverge. And if it's equal to 1, you don't know. And what you put in for these then on the bottom is just, this is an, whatever's here. Limit n goes to infinity. And I'll put 5 times x to the n over n times 2 to the n. That's an just by reading, right? What goes on the top? Same thing with n replaced by n plus 1, right? That's what n plus 1 means. So I'll write the same thing, I'll write, except everywhere I see n, I'll put parentheses. So 5 times x to the parentheses over parentheses times 2 to the parentheses. All right, this is like an represents really a function of n. You can put a of n. This is the function of n that's n times 2 to the n, right? And so this is just the same function, plug in n plus 1. So you put parentheses, put n plus 1, n plus 1, n plus 1 everywhere n was. And that's what the ratio test demands that you calculate, the limit of this ratio. Okay, now we can do a little algebra, right? We can take top times bottom over middle times middle. This will be the limit as n goes to infinity. Absolute value of n times 2 to the n from the very bottom times 5 times x to the n plus 1 on the top over the middle, n plus 1 times 2 to the, this should have said 2 to the n here, times 2 to the n plus 1 times 5 times x to the n. There we go. Algebra, top times bottom over middle times middle. And now you rewrite it a little bit, right? This is the limit n goes to infinity, absolute value, n times 2 to the n times 5 times x to the n times x. I'll write as x to the n plus 1, right? And then on the bottom, I'll keep the n plus 1. I'll write 2 to the n plus 1 as 2 times 2 to the n. And then I've got 5 times x to the n. And by writing it that way, I notice the x to the n's cancel. Pardon me just a second. Okay, just trying to make sure it keeps recording. It logs me off if nobody's on there. And then the 5's cancel. And the 2 to the n cancels the 2 to the n. And what I'm left with then, maybe I better put it up here so you can see it, huh? Is limit n goes to infinity. And now the x and the 2 here can be pulled out, right? There, we're letting n go to infinity. X and 2 are fixed. So I pull out absolute value of x over 2. But the n has to stay inside, right? I'm taking the limit as n changes, so I can't pull n out. I've got n over n plus 1 left. But I can drop the absolute value because they're positive. So I would change it to that. I'll just pull the x, absolute value of x over 2 out. Leave the n over n plus 1 in. And now what's this one? Yeah, it's just one, right? It's quotient of polynomials, a number times a whole power of n plus a number times a whole power of n plus a number over the same. They're the same degree, so it's quotient of leading coefficients. The limit's 1. And then times absolute value of x over 2, which we can write like this. Rho for the ratio test is absolute value of x over 2. All right. Now, what does that tell me? The ratio test tells me that convergence occurs if rho is less than 1. In fact, absolute convergence. Divergence for absolute value of x over 2 greater than 1. Right? And then you rewrite that by multiplying by 2. You get convergence for absolute value of x bigger, less than 2, divergence for absolute value of x greater than 2. What about absolute value of x equals 2? Well, at x equals 2, you just plug it into the original series, right? Original series up there, we got sum n equals 1 to infinity. It should have been 1 to infinity. 5 times x to the n becomes 5 times 2 to the n over n times 2 to the n. And the 2 to the n's cancel when x equals 2, right? And you just get 5 times the sum n equals 1 to infinity of 1 over n, which is what? Yeah, it's a harmonic series, so it's infinity. It diverges, right? When a series of positive terms diverges, it always diverges to infinity because it's adding up to bigger and bigger numbers. All right. At x equals minus 2, I have to check the other endpoint. So what you do in these power series is use the ratio test to find the radius of convergence, which we found here is actually equal to 2. Right? Absolute value of x less than 2 means the radius 2, about x equals 0. And then you check the endpoints separately. So at x equals minus 2, I plug that into the original series. I have sum n equals 1 to infinity of 5 times minus 2 to the n, right? Over n times 2 to the n, just plugging in minus 2 for x. And now that becomes sum n equals 1 to infinity 5 times minus 1 to the n times 2 to the n over n times 2 to the n, and the 2 to the n's cancel now. And I've got, I can pull the 5 out, right? This is 5 sum n equals 1 to infinity of minus 1 to the n over n. And what's that? That's the alternating harmonic series, except by a minus. So it's minus the alternating harmonic series. If I put n plus 1, it'd be alternating harmonic. So this is minus alternating harmonic series, which does converge, right? It converges natural log of 2. So this is minus 5 ln 2 is the sum if I wanted to evaluate it. That one I don't expect you to know. Just this is alternating harmonic. So the point is it converges at x equals negative 2, diverges at x equals plus 2, and now we have the interval of convergence. This here tells you the radius of convergence, right? This is equivalently saying absolute value of x minus 0 is less than 2. Tells you that it converges in the interval minus 2 less than x less than 2. An interval of radius 2 centered at x equals 0, right? That's what radius 2 centered at x equals 0 is what this means. And so this one tells you the radius, and then we check the endpoints. And we have, therefore, this interval of convergence. If you want to draw it, you can write the answer like this. It converges at negative 2 and out to plus 2, but it does not converge at 2. So there's an answer if you want to do a sketch for the answer of the interval notation. And then the radius of convergence is equal to 2 by this statement. Or you can alternatively say, you can give the interval notation or something and say, converges for minus 2 less than or equal to x strictly less than 2 with radius of convergence obviously 2. So either way you can answer this way or this way, right? Or you can use the other interval notation, yeah. Yeah, the closed dot means include that point in the interval, and the open dot means leave that point out, yeah. Uh-huh. Yeah, you can put this form, or you can put this form, or you can put this form if you like, minus 2 to 2 like that also. Round bracket to not include the right, square bracket to include the left. Yeah. All three are equivalent. All right, so that's for power series. What you want to do is usually use the ratio test to find the radius of convergence, then check the endpoints and write the interval of convergence. Uh, 4B, 4D, okay. Suppose I gave you this one, sum n equals 0 to infinity of 7 to the n, x minus 4 to the 2n plus 4. How about that one? What's the interval and radius of convergence for that one? Again, because I see these powers, I'm going to try doing the ratio test. I'll let rho be the limit of the ratio of successive terms. I'll do it a little faster since we just did one ratio test. I put the nth term, an, on the bottom, 7 to the n, x minus 4 to the 2n plus 4. And then on the top, I put the same thing with n replaced by n plus 1. So I'm going to put 7 to the n plus 1, x minus 4 to the twice n plus 1 plus 4. All right. And now I do a little algebra. This is limit n goes to infinity of 7 times 7 to the n times x minus 4 squared times x minus 4 to the 2n plus 4 all over 7 to the n times x minus 4 to the 2n plus 4. And now I can cancel this one with this one. And this one with this one. And I've got 7 times, pull the 7 out since the constant limit n goes to infinity. Can't pull the n out. Actually, there's no n's left, are there? So there's no n's left. This goes to what's left. It's 7 times absolute value x minus 4 squared is what's left. So there's the row from the ratio test. Now we get convergence, in fact, absolute convergence. For 7 absolute value, x minus 4 squared less than 1. All right, row less than 1. Divergence for it bigger than 1. And then we have to check separately at the endpoints. Equivalently, this is x minus 4 squared less than a seventh, which equivalently is x minus 4 between 1 over square root 7 and minus 1 over square root 7. So I'll take the square root of both sides and say they can be plus or minus then. X minus 4 has to be between these two. And therefore, adding 4 through, I get 4 minus 1 over square root 7 less than x less than 4 plus 1 over square root 7. So I get absolute convergence on that interval. Then I can check the endpoints separately. I don't actually need to check the endpoints on this one. At the endpoints, how do I know it diverges automatically? If you don't have the intuition on here, plug in, go ahead and plug in x equals say 4 plus 1 over square root 7. And what do you get? You get a power series, a geometric series. You get sum 7 to the n 4 plus 1 over square root 7 minus 4 to the 2n plus 4. And you get this series, n equals 0 to infinity. And the 4's cancel. And then 1/7 to 2n plus 4, this becomes sum n equals 0 to infinity, 7 to the n. Factor 2 out of here. You can write this 1/7 to the n plus 2, right? 1 over square root 7 to the 2n plus 4 is the same as 1/7 to the n plus 2, right? You just pull a 2 out of here and square this and have n plus 2 left. And now this is a sum, n equals 0. And the 7 to the n, 1/7 to the n cancel. And you got sum n equals 0 to infinity of 1/7 squared. This diverges by the divergence test, divergence theorem, right? Because the numbers are not going to zero. These are not approaching zero. In order for a series to add to a finite number, the limit of the nth term has to be zero, right? The theorem says if the series has a finite sum, then the terms have to go to zero in the limit, and these don't. So diverges by the divergence test. Terms are just adding 1/49 plus 1/49 plus 1/49 plus 1/49 forever, adds up to infinity. Same thing at the other end, but if you recognize that this is actually, right, since the thing is actually a geometric series when you plug it in like this, then you'd already know that at the endpoints. You're just adding the same thing over and over. Same at the other endpoint. So x equals 4 minus 1 over square root 7 similarly. This time you get some minus 1 over 7, I think, squared or something like that. And so it also diverges squared. And let's look at let's look at B also. So that was 4D. Boy, I'm almost out of time here already. As you have other questions, please feel free to come see me. Can't do everything on the test today. Suppose I do this one, 4B. I have sum n equals 0 to infinity. And stay after class as you want or come to my office hour. Minus 1 to the n, x to the n over n factorial. Again, the ratio test is what you want to use for these power series, the ones with x minus x0 to the n in them. What I can do is take rho as the limit, n goes to infinity, with the nth term on the bottom, and n replaced by n plus 1, same thing on the top. Right? And this one, what you have is limit n goes to infinity of top times bottom over middle times middle. And you do the same thing. You try and cancel, except with factorials, what you do is you take the n plus 1 factorial, and you say that's the numbers at 1 through n plus 1 multiplied together. So it's, well, that's n factorial, so it's n plus 1 times n factorial, right? That's the trick on the factorials. So you write this as limit n goes to infinity of n factorial x times x to the n for this one, right? N plus 1 times n factorial replaces the n plus 1 factorial from here. And then I've got x to the n, and now it should be absolute value on these. The x to the n's cancel, the n factorials cancel, and we've got limit of x over n plus 1. We get rid of the absolute value in the n plus 1 because it's positive. You can pull the absolute value of x out because the limit is of n. So it's absolute value of x times limit n goes to infinity of 1 over n plus 1, which is what? 0, right? 1 over bigger and bigger numbers is 0. So rho is 0 regardless of what value of x I pick, right? So what's the radius of convergence? Infinity, right? This is the rho is equal to 0's convergence. You get rho equals 0 for all x. So you get the radius is infinity because it converges for all x. And the interval is n minus infinity to infinity. Let me not keep you anymore. Thank you very much for your attendance today. Best wishes on Monday.